All right, our next lesson is on rate laws. We'll see what a rate law is in just a second. First, let's review what a rate is. Rate is defined as change over time. So again, as we said in the first lesson, it could be change in concentration, change in temperature, change in mass, change in some quantity, but nevertheless change over time. So a rate law actually shows, it's a mathematical equation that shows the relationship between the concentrations of these substances involved in the reaction and rate. Relationship between concentration and rate. So let's go ahead and take a look at this following hypothetical equation. We have A and B that react to produce C and D. And I'm going to put, whoops, I don't do very good with Y's. Let's put Y on top of the arrow. So let's do this. Let's write the rate law, it's called, for this reaction. And so rate law always starts with rate equals K. We'll talk about what that means in just a bit. Rate equals K times concentration of substance A to the A power times concentration of B to the B power times concentration of Y to the C power. So the small letters are the exponents. Those are known as orders. And we'll explain what that means in just a bit. The large letters, those in brackets, those are the chemicals. So notice we have Y's concentration affects the rates. Y is a catalyst. Moreover, it's a homogeneous catalyst. If its concentration affects rate, it must be a homogeneous catalyst. So anytime we put a chemical in brackets, that means concentration, concentration in moles per liter or molarity. So again, A, B, and C are called orders. They are some power. So they could be, for this class, it's going to be pretty easy, but they could be 0, 1, or 2 in higher levels of chemistry. Sometimes those powers are negative. Sometimes they are fractions. But for this class, it'll be a whole number, either 0, 1, or 2. Now, something that is very, very important is that these powers or these orders, these exponents in the rate law, don't necessarily correspond to the coefficients from the balance equation. Now, it just may be coincidental if they are the same, but it's not necessarily how it works. So how about that K in our rate law? K is called the rate constant. It is a constant for a reaction. And the value of a rate constant for a reaction is only affected by temperature. So everything else, all other scenarios remains constant. Only temperature can affect the value of the rate constant. Now, something that we'll have to do is when we're dealing with rate laws is to determine the actual mathematical value for the rate constant. And also, when we calculate the value of the rate constant, we also must determine the units for the rate constant. So I'll show you how to do all of that in just a little bit. All right, so let's talk about these orders. The order of a specific reactant in a reaction is simply the exponent on the reactant's concentration term in the rate law. So we have individual orders and we also have overall order. So the overall order is simply the sum of all the individual orders. The values for each of these exponents or orders may be determined by analyzing a series data in a series of experiments. So you take certain amounts of your reactants, combine them, measure the rate of the reaction, and then you can use that data to determine what effect the concentration of that substance has on the rate. That's the whole goal here, and that's what orders tell you. How much of an effect does changing the concentration of a particular substance have on the rate of the reaction? So let's take a look on page 557. at the example. I'm going to walk you through this particular problem. So let's take a look. So here's our data, and we're going to use this data to determine the order of the reaction with respect to H2O2 and with respect to HI is how we word that. So here's how we do it. We want to do one reactant at a time. And what we're going to do is we're going to take two experiments. We're going to compare two experiments, two trials, they're labeled here, where the concentration of one of the substances is changing and the concentration of the other substance is not changing. Therefore, we can see the effect of just that substance's concentration that's changing on the rate of the reaction. Now, I'm going to need some justification here. So you can do this one of two ways. You can do this with words or with math. I'm going to show you with math. So let's find, which one do you want to find first? Does it matter? Doesn't really matter. So let's find the order for HI first. And so we want to pick two experiments where the concentration of HI is changing, but the concentration of H2O2 is not changing. And so that would be trials 1 and 2. So here's what I'm going to do. I don't like using fractions, so I like numbers bigger than 1. I'm going to take the bigger concentration and divide it by the smaller concentration. So I'm going to take 0.2 molar over 0.1 molar, and I'm going to raise that to the x power. That's going to be our order. And so we take a ratio of concentrations and set it equal to the ratio of rates. So the rate that corresponds to the 0.2 molar is 0.0152. That has units of, oh man, look at that. Here we go again with your book, and it's SI units. Moles per cubic decimeter per second. So mole per cubic decimeter is molar. So this is molar per second, M over S, or M times S to the negative 1. Do the same thing with the 0.1 molar, so its rates, corresponding rate, 0.0076 molar per second. And let's see what we get. So divide those, we get 2 to the x equals, take those and divide them. And what do you get? Now I know what some of you are thinking, oh my gosh, I got to use logarithms to solve. No, not so fast. The numbers will be really easy to work with. So I can tell very easily here that x is 1. So that means that this reaction is first order in HI. All right, let's do the same thing, same process, but let's apply it to our other reactants. So now we want to find the order with respect to H2O2. So this time we want to take two experiments where the concentration of H2O2 is changing, but the concentration of HI is not changing. So that looks like we're going to use experiments 1 and 3, because this is the same and this is changing. All right, so let's set it up again. So we want a ratio of concentrations. I always do bigger over smaller. To the x power, we want to determine what that is and set that equal to a ratio of rates. So when the concentration of H2O2 is 0.2 molar, the rate is 0.0152 molar per second. And when the concentration is 0.1 molar, 0.0076 molar per second. So divide those, we get 2 to the x equals, once again, 2. X equals 1. So that means the reaction is first order in H2O2. So what does that mean exactly? First order, second order, zero order. Let's start with first order. First order means however much you change the concentration by, the rate will change by the same factor. Meaning if you double the concentration of, let's say you double the concentration of H2O2, it will cause the rates to double as well. Or if you double the concentration of HI, since it's first order, the rate will also double. Now, what if you have a reactant that's second order? Whatever you do to the concentration, the rate will change by the square of that change. So if you double the concentration of something that is second order, the rate will increase by a factor of 4. What if something is zero order? What does that mean? Well, think about something to the zero power. What is anything to the zero power? That's just 1. So if you have a reactant that is zero order, what that means is its concentration does not affect rate. So if you double the concentration, you get 2 to the 0. That's going to have no effect on the rate. So that's what those orders mean. So let's then write our rate law. It always starts with rate equals K times concentration of H2O2. We said that this was first order. We don't need to write the number 1, so we'll just leave it like that. Times the concentration of HI, which we also determined is first order. So again, that would get a 1 there, or we can just leave it like that. So again, math or words. So what would words look like? When you double the concentration of HI without changing H2O2, the rate doubles. That means first order in HI. Likewise, when you double the concentration of H2O2 while not changing the concentration of HI, the rate doubles, again telling us first order in H2O2. So either way, math or words, I prefer math. Now, let's go ahead and do this. Let's calculate the value of the rate constant. Now, what did I say is the only thing that can change the value of a rate constant? That's right, that's temperature. Concentrations have no effect on the rate constant. So let's look at our rate law again. Rate equals K times concentration of H2O2 times concentration of HI. So which experiment, which trial are we going to use to determine the value of K? Guess what? Doesn't matter. You're going to get the same answer no matter what. So let's rearrange this equation and solve for K. So we end up with rates over concentration of H2O2 times concentration of HI. What trial do you want to use? Let's use, I don't know, trial 1. Let's plug in our values. So the rate for trial 1 is 0.0076 molar per second. And we want to divide that by concentration of H2O2, which is 0.1 molar. And HI, also 0.1 molar. And we'll get our answer. Now, let's take a look at the units first. One of these molars down here is going to cancel with this one. So go ahead and punch that up and see what you get for the value. We should have 1 sig fig technically in our answer, even though the book shows 2 sig figs. We should get 0.8. What are the units? Well, this seconds, it's a per second, right? It's really on the bottom, and so is this molar. So we end up with this unit, per molar second, 0.8 per molar second, which is the same thing as 1 over molar times second. So either way is fine. 0.8 per molar second. All right, your turn. Go ahead and do some practice. Number 1 on page 558, same, not same approach here, but because we're not using some data, but gives you the rate law this time and asks questions about the substances involved in the reaction and what effect that may have on rate and so on. So go ahead and pause the video and do those now. All right, here's the results. Let me explain them though. For letter A, if the concentration of H2 is doubled, well, if we look at the rate law, the reaction is first order in H2. So if you double the concentration of that, the rates will increase also by a factor of 2. So increase 2 times by a factor of 2, we'll say. Letter B, volume of the enclosing vessel is suddenly halved. If you have the volume, what happens to the concentration? So think about molarity. Molarity equals moles over liters. If you decrease the volume by a factor of 2, the concentration increases by a factor of 2. So you're doubling the concentration of NO and you're doubling the concentration of H2. Well, let's look at them one at a time. If you double the concentration of NO, that by itself will cause the rate to increase by a factor of 4, since it's second order. And if you double the concentration of H2, that will cause the rate to increase by a factor of 2. 4 times 2 is 8. The rate will increase by a factor of 8. What if the temperature is decreased? Well, temperature doesn't affect concentration, but we know that temperature affects rate. How is this possible? Well, temperature affects the value of K. If the temperature goes down, K goes down, and if K goes down, then the rate decreases. So hopefully it did not say slows down. Doesn't say about the reaction. The reaction slows down, the rate decreases. We don't know by how much because it doesn't say how much the temperature is changed by. All right, number 2. This time it's very similar to the one that we worked through. In addition to doing letters A and B, also calculate the value of K. That's letter C here. Calculate the value of the rate constant. Go ahead and pause the video and do that now. Alrighty, here's our answers. To find the order for hydrogen, I would compare trials 2 and 3, where hydrogen is changing and iodine is not changing. So we get 2 molar over 1 molar equals 0.8 molar per second over 0.4 molar per second, 2 to the x equals 2, first order in hydrogen. To find the order of the reaction with respect to iodine, I would compare trials 1 and 2. H2 is constant, I2 is changing. Once again, we see that the reaction is first order in I2. So there is our rate law. Letter B, what if the concentrations of H2 and I2 are both 0.50 molar? Well, that actually happens to be half of what they were for each in experiment 1. So we're decreasing the concentration of H2 by a factor of 2. It's being halved. And we decrease the concentration of I2 by a factor of 2. Again, they're each first order, so we get 1/2 times 1/2 is 1/4. So we take 1/4 of the initial rate of formation of HI, which was 0.20 molar. 1/4 of that is 0.050 molar per second. Molar per second, I should say. Use any of the values from experiments 1, 2, or 3 to find the value of the rate constants. We get 0.20 molar per second. All right, let's try one more. Practice problem number 3. In addition, determine the value of the rate constant as well. Go ahead and pause the video and work on that. All right, so here's what we end up with. So if we want to find the order of the reaction with respect to CH3CO, CH3, I would use trials 1 and 2. They're not numbered, but the first 2 there. Concentration from trial 2 to trial 1 doubles. The rate also doubles. So that means the reaction is first order in that substance. And to find the order of the reaction with respect to I2, I would compare experiments 2 to 3, where concentration of CH3CO, CH3 is constant, and the concentration of the I2 is going up by a factor of 5. It goes from 0.1 to 0.5. When you increase the concentration of I2 by a factor of 5, what happens to the rate? Nothing. So that tells us the reaction is 0 order in I2. So notice I didn't include I2 in here. I guess I could put concentration of I2 to the 0, but we don't need to include that because anything to the 0 power is just 1. Use any data from any trial, or use the data from any trial. We have no iodine to plug into our rate law, so its concentration doesn't matter. And so we end up with a rate constant that has a value of 1.16 times 10 to the negative 6. Units are per seconds. So keep in mind on top you have molar per second. On the bottom you have molar. The molars cancel. What are you left with? You're left with just per seconds. All right, that concludes this lesson, and in fact, it concludes this unit. Thanks for watching.